Well, welcome back, everyone, and again, thanks for coming. Now what I'd like to talk about is, let's suppose you've done a randomized controlled trial. You've collected the data. Now you're at the fun part, doing the analysis. You spent all these years preparing, designing this study, implementing the study, collecting the data. Now the fun part begins. Let's see what the answers are. Let's see if one treatment is performing better than another treatment. Let's do the analysis. So I want to talk about the types of analyses you might do in randomized trials. Well, here's a diagram that's somewhat similar to the one I showed when I first introduced the notion of a randomized controlled trial. Remember, that was a trial comparing a new treatment versus some standard of care. And I made the point is we take subjects and we randomize them to either receive a new treatment or receive a standard of care. And if it's a large study and you're using simple randomization, these two groups, those who receive the new treatment and those who receive the standard treatment, should be very comparable to one another. Equally old people should be randomly assigned to one treatment versus another treatment. If it's a small study and you stratified by age and did block randomization, again, equally number of old people will be put into the new treatment arm as into the standard treatment arm. That's what randomization buys you. It buys you comparability. But then I talked about post-randomization problems. I talked about compliance. So let's suppose in the people who were randomly assigned to receive the new treatment, that not everyone complied with their treatment. They were supposed to take this pill every day, but only some of the people actually did this. And when you ask them about their compliance, let's suppose capital A of those people said, yes, I'm compliers, and capital B says, no, I decided not to take the pill. Those are the problem individuals that I'm concerned about. Among the people who received the standard of care assignment randomly, let's suppose the same thing. Some complied, that's C, and some that didn't comply, that's D. Now, what we're going to do is measure outcomes on these people, so everyone's being followed over time to develop outcomes. But the question is, which groups are you going to compare if this is your study design? Are you going to compare everybody who's assigned to the new treatment versus everybody who's assigned to standard of care? Or are you just going to focus on the compliers of the new treatment versus the compliers of the standard of care? Because if the new treatment has any benefit, it's only going to be seen among people who take the new treatment. And that might be arguing for just doing analysis based on the compliers. Well, let's talk about the merits of these two different analysis schemes. The first one is called the intention-to-treat analysis. That means we're going to compare everyone who's randomized to receive the new treatment to everyone randomized to receive the standard of care. So in the previous slide, intention-to-treat is going to compare everybody randomized to the new treatment versus everybody to the standard of care treatment. It's going to compare the A plus B people as a group versus the C plus D people as a group. That's what the intention-to-treat, because intention-to-treat means which group you are randomized to. So intention-to-treat compares everybody randomized to receive the new treatment versus everyone randomized to receive the standard of care. It's the most valid comparison you can do with these data because it takes into account the role of randomization. Randomization means before people start taking their pills, comparable people are assigned to a group who received the new treatment, the A plus B individuals, to the group that received the standard of care, the C plus D people. That means at the beginning of my study, I have two groups that are comparable with respect to age and sex and other risk factors that might influence the outcome, other potential confounders. So it's the most valid analysis you can do. The problem is when you do this analysis and measure the association, comparing everybody who received the new treatment to everybody who received the standard of care, compliance is going to hurt you. If very few people randomized to receive the new treatment actually took the new treatment, if the A group is very small compared to the B group, then the group you're saying randomized to receive new treatment unfortunately doesn't have much of the benefit that the new treatment might have because fewer people are actually being given that, are taking advantage of that treatment assignment. And the same thing can be said among people who were receiving the standard of care. So the existence of these non-compliers, B and D, means that only part of the group are going to get the benefit of one treatment versus the treatment that's assigned to that group. And as a result, the measure of association you calculate when you do a intention to treat analysis might not be reflecting the true benefit of the treatment if you have non-compliers. If the reason for non-complying in either groups is not related to the outcome, in other words, if non-compliance is sort of a random event, then what happens is what we see as a measure of association is really going to underestimate the true benefit of our new treatment. And that's the downside of an intention to treat analysis. It might be the most appropriate from a validity point of view, but from an interpretation point of view, if you have lots of people who are not complying, and if compliance has nothing to do with expected outcomes, then the value you get from your measure of association probably underestimates the true benefit that the treatment would have if everyone took the treatment, if everyone had complied. So that's the plus and minuses of the intention to treat analysis. The alternative is what we call an on-treatment analysis. It's a subset analysis. Let's just look at the people who actually took the treatments they were assigned to. Let's compare the A people who were assigned to the new treatment, who actually took the new treatment, versus the C people who were assigned to the standard of care, who actually took the standard of care. Well, here we're comparing people who were assigned and accepted their assignment. We're comparing people who actually received the new treatment to actually receive the standard of care treatment. It improves the chances of showing the benefit of the new treatment over the standard of care. But the problem is this subset analysis is no longer using everybody. It's not reflecting the original randomized controlled trial. It's not reflecting the lack of confounding, the comparability that the randomization gave you. It may well be that the people who complied with the new treatment, the A subgroup, are old people. It may well be that the people who complied with the standard of care were young people. So what we're doing when we do this on-treatment analysis, we're comparing old people who took treatment A versus new treatment versus young people who took the standard of care. That's a potential problem, potential confounding problem. So the big disadvantage of the on-treatment analysis is it does not account for, take into all the power, all the positive benefit of randomization. It's an observational study. And we'll talk more about observational studies in the next two sequence of lectures. And essentially that's all we're doing. We're giving up the randomization component of the trial we did, looking at a subgroup analysis, compliers only, which is now no longer benefiting from the potential of randomization to give me comparable groups. So those are the two first questions to ask: what type of analysis you're going to be doing, intention to treat versus on-treatment analysis. The last thing I want to talk about is let's just think about the tables you're going to be creating in this paper you're writing. Your first table in randomized controlled trials and in observational studies also, table 1, is often a table that compares the characteristics of the people who receive who are randomized to receive treatment A or the new treatment versus people who are randomized to receive treatment B or the standard of care. So what you have in this table essentially is a column that has at the top of the table whether you're randomized to receive new or standard of care, and you'd have for everybody in each of the groups more or less what the average age is. You're showing the reader that the average age in the people who are randomized to receive the new treatment might be 45.1 years of age. The people who are randomized to receive the standard of care might be 45.3 years of age. If you're doing a large randomized trial, or if you're block randomization after stratifying by age, you're going to expect to see similarly old people in the two groups you're comparing. Same thing if you look at the percentage of people who are men. You might see 43% in the new group who are receiving this new treatment versus maybe 41% in the standard of care. So the first table is to show the reader how comparable your two groups are with respect to factors that might influence your outcome, with respect to potential confounding factors. And what you expect in a randomized trial, especially if it's large, is balance. We can look down the column to look at the distribution of these various factors among people who receive the new treatment and compare it to the distribution of people who were assigned to the standard of care treatment, and see how similar they are, and you expect them to be similar. If it's a small study and just by the unluck of the coin flick, if more old people were given the standard of care than given the new treatment, we can still adjust for factors that are not imbalanced, as we would do in an observational study. But Table 1 gives the reader an idea of how balanced your two groups are. And in a large randomized study, you're almost guaranteed that things will be balanced. And I'll show you an example of a Table 1 in the next lecture when I give you an example of a randomized controlled trial. Now, Table 2 in a randomized trial is usually your result table. You're reporting the risk ratios, the odds ratios, when you compare everybody who are randomized to receive the new treatment versus everyone who is randomized to receive the standard of care. You calculate some measure of association, a risk ratio, an odds ratio, or something like that. Usually, that analysis is based on an intention to treat analysis, comparing everybody randomized to receive the new treatment versus everyone who's randomized to receive the standard of care, taking advantage of what randomization gave you, the balance that you saw in Table 1. Now, if you have balance in Table 1, this unadjusted analysis is probably sufficient to describe the valid result or the valid effect of this new treatment versus standard of care. You typically do not have to adjust for factors, adjust for confounding, because everything would probably be balanced in a large randomized trial. So typically in Table 1, in Table 2, you would report risk ratios, odds ratios, rate ratios, whatever your measure of association is. And along with that, you'd report either p-values or confidence intervals, things we discussed last time in the last sequence of lectures, as some measure of statistical inference, some idea of how generalizable your results might be. So that's what Table 2 would give you. Now, Table 3 is often a table where you talk about the effect of your treatment in certain subgroups. You might just compare men who were randomized to receive the new treatment versus men randomized to receive standard of care, or old people who received the new treatment versus old people who received the standard of care, or maybe people with very severe disease who received the new treatment versus very severe disease who received the standard of care. So typically you could list those subgroups for which you are interested in seeing if the treatment works in that subgroup, or whether it works better in that subgroup than it does in general, or whether it works worse in that subgroup than it does in general. Now, the only recommendation I have is you should specify these subgroups up front before you do any analysis. When you're first designing the study, you should specify in the protocol, the design of this randomized trial, when I come to the analyses, these are the 5 subgroups I want to look at, because I'm interested in knowing whether this treatment works better among men than among women, or works best among old people, or something like that. What that would do is it avoids a potential problem. We can call it data dredging. Some people used to call it data mining. Maybe a better word is fishing. This is the temptation all we epidemiologists have. The data is now collected, and I have spare time on my hands now. Let me look to see if there are other subgroups that I originally had not anticipated as being important subgroups to look at. They weren't specified in the protocol. But now, since I have information on it, let me see if this treatment works differently or works best among men who are under the age of 35 years of age who have a college degree. And there are many subgroups I could create after the fact using the data I've collected. And in some of those subgroups, I might find that the treatment has a better outcome. The new treatment works better than the standard of care. Those hypotheses, those subgroups, were not specified up front. And the problem is that if I look deep enough, sooner or later I will find a subgroup just by chance alone where the treatment is going to work very much better or very much worse, the new treatment, than the standard of care. And the problem is that might just be an artifact, an idiosyncrasy of this one data set that's not going to hold up in other data sets. So I don't want to use this data set for 2 purposes: to go fishing to see if I can find these subgroups first, and then declare how important they are by reporting their measures of association, their p-values and confidence intervals, and say, aha, among young men under the age of 30-something who have college degrees, this new treatment doubles your chances of surviving 5 years down the line. That's a big effect. But it's one of many, many effects I looked at in this data set. And the problem, I've used this single data set for two purposes: to search for these subgroups, to report the ones that were the most important, and then to make a big point. This is the subgroup that had the biggest effect. Really what I need is another data set, because what I have done is I've generated hypotheses, potential points for consideration for future studies. In a future study, I could see if young men with college degrees, whether the new treatment works better than the existing treatment. But I don't want to use a single data set to both look for these associations and declare how important they are. This is related to the statistical problem of multiple testing, which is maybe something that Marcello Pagano will talk about. Essentially what it says is the following: when you do a test of significance and the null hypothesis is true, there's a 5% chance you'll get a p-value less than 0.05. There's a 5% chance of finding a statistical significant result just by chance alone. So when you start declaring all your statistical results, realize that some of them are just false positive results, things that happen just by chance. The more tests you look at, the greater the probability is of finding a statistically significant result just due to chance alone. So there are statistical techniques that try to penalize you for the number of tests you're doing. That's what multiple testing involves. And that's something you'll learn more in statistics and the statistics part of this course. But as a general rule, subgroup analyses are fine as long as they're pre-specified, and essentially keep them to a minimum. Don't go fishing too deeply into your data set. Well, that's what I wanted to say about analysis of randomized controlled trial. In the next time, the last lecture in this sequence, I want to give you an example of the development and the analysis of one randomized controlled trial, the Physician's Health Study. See you then.